Hi students, today we can discuss the chapter Metals and Nonmetals, chapter 3 of class 10 chemistry. Okay, today in this video we'll be discussing the physical and chemical properties of metals and nonmetals. See, the physical and chemical properties, elements are classified as metals and nonmetals based on their physical and chemical properties. So the easiest way to start grouping substances is by comparing physical properties. So first we will talk about or we'll discuss the physical properties of metals and nonmetals. Okay, coming to the physical properties of metals. So first we learned in this lower classes metallic luster. That means a shiny appearance for a newly cut part of the metal. Okay, these are examples given: aluminum, copper, silver, etc. Showing shiny appearance. Then we know they are all very hard. The hardness of metal is very important to be noted. But there is an exception: sodium and potassium are soft metals. Okay. Then malleability. It is the property of the metal to be beaten into thin sheets like this. So metals can be beaten into thin sheets like this. Okay. Gold and silver are the most malleable metals. So next property is ductility. That means the ability of metals to be drawn into thin wires like this. Okay, can be drawn into thin wires. See, gold is the most ductile metal. 1 gram of gold can be drawn into a wire of about 2 kilometer length. Okay, and so gold is the most ductile metal. And due to malleability and ductility, metals can form different shapes. Conductor of heat. Most metals are conductors of heat. Here is an activity given here. Allow a metallic wire to stand like this. In a stand you set up. Then at the tip of the metallic wire you can fix a nail using wax. The other end of the metallic wire can be heated using a burner. And after some time we can see that the pin is coming down due to the passing or due to the conduction of heat through the metallic wire. Okay, so metals are good conductors of heat, which can be proved. Then silver and copper are the best conductors of heat. Silver and copper. Lead and mercury are the poor conductors of heat. Okay. Conductor of electricity. So metals are usually good conductors of electricity. This activity or this setup arrangement will help you to find out whether a metal or is a conductor or heat, conductor of electricity. A battery, and if the bulb glows, if you connect the piece given to you in this clip, between these clips, the bulb will be glowing. If the bulb is glowing, it means it's a conductor. So when you test that, you can find that our metals are good conductors of electricity. Then sonority. Sonority means the ability to produce sound on striking the hard surface. So metals are usually sonorous and they are used to make bells like this. Okay. Then coming to non-metals, there are only very few in number. Carbon, sulfur, iodine, oxygen, hydrogen, chlorine, etc. are examples of non-metals. Usually non-metals are solids or gases except bromine, which is liquid. Okay, only very few non-metals have some physical properties of metals. For example, graphite is a non-metal which is hard substance like metal. Coal is a non-metal which is hard again like metal. Sulfur is a nothing special about, but iodine is having metallic luster even though it is a non-metal. Okay, so these are some of the exceptions which you can find among non-metals. And some more examples are given for the exceptions in the case of metals. Mercury, a metal with liquid state. This is gallium and cesium. The gallium, you can see it melts on the palm. Usually metals are having high melting point, but gallium melts on the palm. Then see iodine, even cesium also having very low melting point. Iodine is a non-metal, but it is having metallic luster. Diamond, it's made of carbon, which is a non-metal but have luster, very shiny appearance. And see, sodium is a metal which usually our metals are hard, but sodium we can cut even with a knife. These are some of the exceptions you can find in among the metals and non-metals. Okay. Then coming to chemical properties. Elements can be more clearly classified based on their chemical properties. Okay. For example, magnesium. Magnesium is a metal which burns in air forming magnesium oxide, which dissolves in water gives you magnesium hydroxide, and it is basic in nature. So metallic oxides are basic in nature, we learned. Whereas sulfur is a non-metal, bonds in air, you get sulfur dioxide, dissolves in water, you get sulfurous acid, which is acidic. Okay, so non-metallic oxides are giving acidic substance, or they are acidic in nature. Okay, so we can conclude metallic oxides are basic, whereas non-metallic oxides are acidic. Now, what happens when metals burn in air? So, see, sodium metal burns with the vigorous flame, magnesium with a dazzling white flame, sodium with an yellow flame, copper with blue flame, aluminum with bright white. Okay, so these metals burn in air, but the sodium burns easily. Magnesium is burns easily, but not that as easy as sodium. So the ability to catch fire is vary to, according to the reactivity. Okay, and the products obtained, the oxides obtained are, in the case of sodium and potassium, they are soluble in water. All others it is insoluble. All other oxides are insoluble in water. Okay, then what happens? We continue. Metal plus oxygen gives metal oxides. Copper, what happens is heated in air forms copper oxide, a black coating on the surface of the metal. Similarly, aluminium forms aluminium oxide. So metals on reaction with oxygen forming metal oxides. Okay, if they are not burning, they can combine with oxygen. Okay, even without burning, they'll change into the corresponding oxides. Few metals like sodium, potassium, magnesium, etc. Catches fire very easily, whereas this form their oxides on the surface of the metal. Okay, then most metal oxides are water soluble, but sodium and potassium are water. They are water soluble, others are water insoluble. Sodium and potassium oxide, so it dissolves in water, giving the sodium hydroxide and potassium hydroxide respectively. And made sodium and metal and potassium metal reacts vigorously with the air. Okay, if you keep in the open air, it catches fire. So they are kept in the kerosene. Sodium and potassium are kept in kerosene because they catches fire easily. They catch fire easily when kept in open. Okay, so to avoid that, we are keeping them under kerosene. Now, burning of magnesium, iron filings, it is showing here. Ordinary temperature, the surface of metals like magnesium, aluminum, zinc, and lead, etc., are covered with a thin protective layer of oxide. It prevents further oxidation. Okay, iron does not burn on heating, but iron filings burns vigorously when sprinkled over a flame. Okay, copper does not burn, but forms a copper oxide layer over on the surface of the metal. Silver and gold do not react with oxygen even with the high temperature. Okay, so the reactivity decreases, you can see. Now there is a anodizing is a process where we are converting or making an oxide layer over the metallic surface. The process of forming a thick oxide layer of aluminum. This to improve the resistance against corrosion. Okay, in this what we are doing is a clean aluminum article is electrolyzed with dilute H2SO. That is what is shown here. Even though it is not clearly given in the text, you can understand that this oxygen gas, see in this setup, the rod to be anodized should be taken as the anode, and after some time you can see that it gets a coating of aluminum oxide over the surface of it, because on electrolysis oxygen will be produced. It reaches here that anode and reacts with the metal to form the aluminum oxide on the surface of the metal. Okay, this process is called anodizing. Okay, which in turn can be uh, dyed to into different colors so that it will not corrode at all. Okay, so it's a method to prevent oxidation, or a method to prevent corrosion. We'll study later in this chapter. Okay, what happens when metals react with water? See, some metals react with water from metal oxide and hydrogen gas. Metal oxides dissolve in water, we know. Mm. Then, uh, see, it is given potassium burns. If you drop a piece of potassium in water, it catches fire. Same is the case with sodium also. If you drop a piece of sodium in water, it catches fire like this. Now why? Because this reaction of sodium to potassium with water is highly exothermic. So the gas produced, hydrogen gas produced, catches fire. That is the reason for the flame. Okay, so the hydrogen gas produced catches fire due to the heat liberated during the reaction. It's a highly exothermic reaction of sodium and potassium with water. Okay, then calcium. Now, so keep in mind, sodium and potassium reacts vigorously, very vigorously with water. Now, coming to the next element, calcium, it reacts less violently, but it forms bubbles on the surface of the metal, which makes it float on the metal, float on water. Okay, calcium floats on the water because hydrogen gas bubbles stick to the metal surface. Magnesium do not react with the cold water but react with the hot water. See, you can see that vigorous nature is coming down, or the reactivity is decreasing. Sodium potassium highly vigorous. With the calcium it is less violent. With magnesium it will not react, but with hot water it forms and floats on water. Okay, gas bubbles stick into the metal and it makes the magnesium float on water, hot water. Okay, now coming to the next element, aluminum, iron, and zinc. They do not react with the cold, hot, but with the steam only. Okay, so with steam, aluminum and iron react to form their corresponding oxides. And metals such as lead, copper, silver, and gold do not react with water at all. So if you take sodium, potassium, calcium, magnesium, aluminum, iron, then lead, copper, silver, gold, like it goes. Okay, that means this is the decreasing reactivity. You can see that reactivity of metals with water is in decreasing order is given here. Okay, now what happens when metals react with acids? Metals react with acids to give salt and hydrogen gas. Salt and hydrogen gas. But all metals do not react in the same manner. For example, put aluminum, copper, iron, lead, magnesium, and zinc separately in test tubes containing dilute hydrochloric acid. Suspend thermometers so that the bulbs are dipped in the acid. The following reaction occurs. So in the case, if you take all these metals, you can say magnesium, aluminum, zinc, and iron only react with the hydrochloric acid and producing hydrogen gas. Okay, whereas copper and lead do not. Copper does not react with the dilute HCl, so no bubbles will be produced. Lead also will not react. Okay, so generally we can say that most of the metals react with the acids producing salt and hydrogen gas, but hydrogen gas is not evolved when a metal reacts with nitric acid. What is the reason? It is because nitric acid is a strong oxidizing agent. So what it is doing? It oxidizes the hydrogen to water and itself gets reduced to nitrogen oxides like N2O and nitric oxide and hydrogen dioxide. Okay, so but magnesium and manganese react with very dilute nitric acid evolving hydrogen. So keep in mind this magnesium and manganese react with very dilute nitric acid evolving hydrogen. Okay, very dilute. So usually hydrogen gas will not be evolved with the metals due to the high oxidizing power of nitric acid. Okay. Now there is a special solution called aqua regia, which is called a Latin. In Latin, the meaning of the word is royal water. Okay, this is a mixture of concentrated hydrochloric acid and concentrated nitric acid in the ratio 3:1. Okay, so this solution is called aqua regia. It is called royal water because it can dissolve royal metals like gold and silver, gold and platinum. Okay, see the picture shows we are keeping a gold metal piece into aqua regia. It is the color is increasing. You know why? Because this gold is getting dissolved in it. Okay, so aqua regia is a mixture of concentrated HCl and a concentrated HNO3 in the ratio 3:1. HCl is more in quantity. Now, how do metals react with the solutions of other metal salts? Okay, the salt solution. We learned these examples in the first chapter, types of reactions, in the type displacement reaction. So the displacement reaction is taking place when metals will react with the solutions of other metal salt. Okay, metal salt. For example, here it is given iron plus copper sulfate, iron, sulfur, and copper, displacement reaction. So the important thing to be kept in mind is more reactive metal only can displace a less reactive metal. Okay, that we discussed before. See, here is an example once again given. Copper sulfate solution, which was blue in color, is changing into green due to displacement of copper from, and the iron nail is getting a reddish brown coat of copper. Okay, so copper get displaced is getting deposited over the iron nail, whereas the solution copper sulfate changes into ferrous sulfate, changing from blue to green. Okay, so combining or keeping all the reactions in our mind, we can have the can not to make the displacement reaction easy, we can keep this reactivity series in our mind. The reactivity shows the metals in the decreasing order of the reactivity. Potassium, sodium, very reactive metals, calcium, magnesium, aluminum, zinc, iron, almost same way. Then lead, copper. Below hydrogen, it is the royal metals, mercury, gold, and silver are there. Okay, so this is the reactivity series which helps us to check whether a reaction will be taking place or not. Okay, so that's all for this video. Next topic will be continuing in the